Hello everyone. So we are both PhD students working in the same research group in the University of UC Louvain in Belgium, under the supervision of the professor Rafael Jongers. And so the goal of our package, Dionysos.jl, is to provide a modular platform for smart symbolic control. So thanks for coming, because it's a more specific talk, but even for people who are not familiar with the topic of control, it's a nice example of how we leverage the powerful ecosystem of Julia to implement the theoretical tools that we are developing in our research team. So first, what's control? So as you know, the idea is to control a dynamical system, such as, for example, the drone evolving in a complex environment. It could be a city with buildings. It could have also external disturbances, such as the wind. And you want to control the system, for example, from one point to a target while avoiding an obstacle, for example, the buildings. And what we want is to provide a generic procedure to design such a controller with formal guarantee. So, as you know, in the last century, control theory had enormous success for controlling physical systems, such, for example, the watt regulator. And this kind of system, it was possible to describe them with, let's say, simple models with different linear differential equation. And we have a lot of powerful mathematical tools to control this kind of systems. But nowadays, the systems are becoming much more complex, such, for example, for bipedal robots, etc. And it's more a question. It's not so a question about the dimension of the systems. So let's say the number of variables describing the dynamics of the system, but it's more a question about the nature of these systems. Because now systems are more with an hybrid nature, where you have the continuous evolution of the system, coming from the physics of the system, that interacts with a discrete part, for example, coming from the controller, for cyber actuators, etc. And so it's what we call the cyber-physical paradigm shift. And to describe these new systems, we need much more complex model than differential equation that will, in fact, combine differential equation with automaton theory. And so through this presentation, I will first describe the origin of the project, then I will describe the kind of techniques that we design in this toolbox. Then we will go through the toolbox, and before concluding, we will present some benchmarks. So the origin of the project is an ERC project called L2C, so Learning to Control. And so the idea is to have an approach which is based on the state space description of the system, but I will present this more in details in a few minutes. So what's the kind of algorithm that we want to use? Is what we call abstraction-based control. And the idea is, so sometimes your original system, so let's say, for example, the drone, is too complex to try to develop directly a controller to satisfy your specification. And typically, the original system has an infinite number of states. And so you have also your original specifications. And so the idea is we will abstract both the original systems and the specification into a new system and new specification, such that they will be composed of a finite number of states. And so now we obtain a new control problem on a finite state automaton with new specification. And so there exists a lot of powerful algorithms to control this kind of system, because it's really coming from graph theory, such as A-star, etc. And so the idea is, then we will solve this symbolic, so discrete problem. And then, before we abstract, in fact, the system in a very specific way, we will be able, from the controller of the discrete model, to refine it in a controller for the original system. And so it's more than just obtaining a finite version of the system, a new representation. Then we will be able to refine the controller for the original system while still satisfying the original specification. And so how we construct in practice this finite representation of the system. So let's say that you have a two-dimensional state space system. So for example, you have the position on the x-axis and let's say the velocity on the y-axis. And so there is an infinite number of states, because for each couple of points, it characterizes a state of the system. And so how we will abstract the system, for example, we could simply discretize the state space with a simple grid. And then for every cell in the grid, we will associate one node in a graph. And then for every cell, what we could do is to apply the finite input during a finite time step, And we will over-approximate the image of the dynamics under this input for during this time step. And so, for example, is the set in red, but it could be complex, so we can compute an over-approximation of this set. And then, in the abstraction, what we will do, we will add a transition to all the cells that have a non-empty intersection with this set. And so, in some way, with this, so the result that we obtain is a graph. And in some way, it contains all the behavior that the original system could contain, but even maybe more behavior, because we discretize, since we discretize the state space, we lose the precise information where we are in the cell. And so that's why we have to add a non-deterministic transition in the abstraction, because we don't know precisely where we are in the cell. And so I have to consider that I could reach any of these nodes in the abstract model. Okay? And so with this process, we have two, I would say, main drawbacks. First, okay, we add non-determinism in the new representation of the system, while maybe the original system was deterministic. And the second drawback is, of course, what we call the curse of dimensionality. That is that the number of states in our abstraction will grow exponentially with the number of states variable. And so for that, okay, it's here another example that's in order to reduce the non-determinism, instead of in the previous slide, I told you that we apply the finite input. What we could do is also to design local controller. That is that we will exploit the concrete state, the information, the state information of the original system. So for example, here I use a constant input for all the cells. And so if the system is not stable, that is that the trajectory will in some sense diverge, I will bring a lot of non-determinism transition in my abstraction. While if I am able to design a local controller that will in some way compress the image of the cell, I can manage the non-determinism and construct an abstraction that is, for example, a deterministic graph, so a simple graph. And so when I will have to solve the abstract problem, this process will be easier with a deterministic graph than for a non-deterministic graph. And so, since the main problem of this approach is the curse of dimensionality, what we want to do is to avoid to construct this abstraction entirely on the state space. Maybe we could only discretize a small part of the state space that is relevant for the specific control task that we want to solve. And the second way to tackle the problem is also, instead of using a simple grid to discretize the state space, we could try to design non-uniform cells, for example, here in blue, in order to reduce the number of states in the finite state representation of the system. And so now we arrive to the goal of Dionysos. So what we want with Dionysos is to, given the complex representation of the model, for example, the bipedal robot that I gave at the beginning, what we want and the specification that you want to reach, the goal of Dionysos is to provide you both an abstraction of your system, so a new representation of your model, with a finite number of states, and the controller to solve this specific control task. So here mainly present the main contributors of this project. So I would like to thank Benoit, Guillaume, Lucas, Adrien, and Virginie. So all these people were at some point members of our research team. And so no, okay, so Dionysos, so it's code in Julia. And in fact, it leverages a lot of the ecosystem of Julia. For example, we use a lot Julia reach in order to compute the over approximation of the reachable set that I mentioned before. We use also JuMP, because as you will see more in details after, we describe in fact a problem, a control problem, exactly in the same framework that the control problem, an optimization problem in JuMP. And instead also of defining a solver to solve an optimization problem in JuMP by implementing the optimizer interface. In fact, in Dionysos, the optimizer will be a solver to design the controller. And so the optimizer of JuMP will provide us the abstraction and the controller of for this specific control problem. And we also use Julia Robotics, for example, in order to design the model of the system that we want to control. So now I will give the floor to Adrien.
So yeah, thanks a lot, Julien. So now let's dig into the structure of the package itself in Julia. So the package is centered around different modules, and so for the sake of the presentation, I will just focus on the three main modules of our package, which are problem, system, and optim. And as Julien said, we really use all the existing packages in Julia, such as mathematical system, hybrid systems, and JuMP and MathOptInterface, but I will go into more details afterward. So okay, let's start with the system module. So the system module really contains all the definitions of, so all the structures needed to define mathematical dynamical systems. Okay, so it contains descriptions of control dynamical systems, but also of some controllers. And it also contains some methods. So for example, the Runge-Kutta scheme, which allows us to go from continuous dynamical system to discrete times thanks to derivation. And as I said, it's built on top of existing packages, and the two packages that we use in this module are mathematical systems from Julia Rich and hybrid systems that Benoit wrote, which is an extension of mathematical systems. So now we have the problem module. So the problem module, it's really used to define the control problems. And so for now, we handle two types of control problems, which are optimal control problem and safety problems. And so these two are really two classical problems in control theory. The first one is you have an initial set, a target set, and you have some costs to go from one state to the other, and you want to minimize the costs to go from the initial set to the target set. And the second one is a bit more general and contain safe and unsafe sets. And you want to have a guarantee that you will reach a safe set and that you will avoid an unsafe set. And so each problem is actually composed of a system. So that's defined in the system module, and the specifications of the problem, such as the initial set, the target set, and the cost. And now the optim module really contains all the methods that we use to solve these control problems for the specific systems. And so here you have the list of all the methods we have. So we have 5 different methods based on abstraction-based control, so that Julien introduced. But we also have other methods to solve optimal control problems. And so this module is based on MathOptInterface and JuMP, because such as Julien said, every method that we use to solve the control problems are actually defined as optimizers in the same framework as in the optimizing package of Julia. And so I will go a bit more into the details, but basically every optimizer is a subtype of the abstract optimizer type of MathOptInterface. And so each optimizer is composed of the problem with the specifications, which itself contain the system and the method specifications. Okay, so just to go a little bit into the details of how we write the methods as optimizers. So as I said, we define the optimizers as structures that implement the abstract type of JuMP. And so, for example, for this optimizer, we have the concrete problem, the abstract system, the abstract controller, and the concrete controller, which are all the steps needed to solve the abstraction-based problem. And so, for example, in this one, we would also need a state grid and an input grid, which are the grids that you saw with Julien in the first slides. So this is an example of an optimizer that we could write in our package. And then we would have to implement the optimize function for MathOptInterface, which basically solves the problem. So without going into more details, this code only does exactly what Julien said. So building the abstraction, solving the control problem in the abstract world, and then refine it to a controller in the world of the initial dynamical system. So now we focus on 2 examples. So first, we want to show you an implementation of an abstraction method that we developed in our research team, but we also implemented in Dionysos existing methods from other research teams that are a bit older. And so the second example is an implementation of an abstraction method from the state of the art, and then I will benchmark this implementation compared to existing implementation of those methods. So the first example concerns a very simple discrete time dynamical system. So without going into the details, it simply describes a state that's translated by an input, and it's in 2 dimensions. And the control objective is to drive the state from an initial set to a target set while avoiding obstacles. And so this is an optimal control problem as defined in the problem module. And so for that, we will use a smart abstraction method that's called hierarchical abstractions that Julien developed 2 years ago. So what does it look like in Julia? Well, first we have to define the system. So this is only pseudocode, so you don't have to look really into the details of that, but basically you have to first define the system. And so here, a simple system is an implementation of a mathematical system. So it's just a description of mathematical systems. So it contains the description of the system I presented in the last slide. And then we define the optimal control problem with the specifications, such as the initial set, the target set, the costs from going to one state to another, and the cost to be in one state. And then finally, we define the method that we use to solve this. And so this method is already implemented in hierarchical abstraction, so in our Dionysos package. And so we just instantiate this optimizer. And then we set to the optimizer all the attributes it needs to perform. And then finally, we just call the optimize function. So this is really just exactly the same as you would do if you use JuMP to solve an optimization problem. And then, for example, after we can extract the abstract system if you want to have a look at what the abstract system looks like. And so if you want to have the full example, you can go to the documentation of our package, and you will find in hierarchical abstraction the full example. And here is a visualization of the result for this specific problem. And so I also wanted to take the opportunity to say that everything has been implemented with recipes. I don't know who knows recipes in the room. So if you don't know recipes, it's a very nice package in Julia that allows you to define how you have by default to plot a structure in Julia. And so here it's very simple because with one line of code we can plot this because we have defined by default how to plot our solution. And so we use that for all of our problems, implemented problems and implemented methods. Okay, so a second example, it's another dynamical system, but it's the dynamical system that represents a vehicle that moves in the 2D plane, and the input is the rear wheel velocity and the steering angle. And then, again, the control objective is to drive the vehicle from an initial position to a target position while avoiding obstacles. So it's the same problem as before, but for a different dynamical system. And we will use, to solve this problem, another method, so another optimizer, which is an abstraction method from the state of the art that's described in this paper from 2017. And so, again, what does it look like in Dionysos? Well, same. First, we instantiate the optimizer, and then we set to the optimizer every attribute it needs. So, for example, here it needs the concrete problem, and then it also needs, for example, the state input and the state grid and the input grid, which are what Julien defined in the beginning of the talk. And then we solve the problem just by calling the optimize function from MathOptInterface. And then again, we can use the getters and setters function from MOI, and so that's also one advantage of using the same framework, because we don't have to rewrite all those getters and setters functions. And so again, we can very easily plot the trajectory thanks to the recipes we have implemented for this problem. And again, if you want to have a look at the full example, it's in the documentation. Okay, so here is a comparison of our implementation versus other implementation. So this is an implementation of the last method, so the method of the second example, and you can see that our implementation really outperforms the other implementations, and Yeah, and this is another example where you see that again it takes really much less time to compute the abstraction and to solve the problem than other existing implementations. And this is due to the fact that first it's implemented in a smart way in Julia, so we really try to optimize the code as much as possible, but also because we use different data structures. So the implementation itself is not really the same. Okay, so here is also a summary of the different abstraction method we have implemented for now in Dionysos. When it's called lazy, it's where we don't cover the whole state space. So that's what Julien was referring to when you don't want to cover the whole state space, but you just want to cover the state space along a trajectory. That's what we call lazy. And some use hyperrectangles. So that suffers from the curse of dimensionality, but others use ellipsoids, and so these are just different ways of partitioning or covering the state space. Okay, and here is the recipe for each of the methods that we implemented. Okay, so before concluding the talk, I just want to tell you about the orchestrator. So that's an idea that we want to implement that's not implemented yet. But the idea is that, okay, we have some solvers that I just described. We have different problems. The idea is to have really as many problems as we can. So define many different problems. And we can always measure some features such as the execution time, the memory consumption, and the optimal cost. And the idea would be to somehow make an orchestrator learn the optimal solver to use and the optimal metaparameters to use for a specific problem. And so the idea in the end would be that we give a problem to Dionysos, and that Dionysos chooses automatically the right method to solve the problem. And so to do that, we would have to implement many different problems and then use learning techniques such as, why not, neural networks or other statistical learning methods to train this orchestrator and then to have it implemented in Dionysos. So in summary, we have that Dionysos, it implements both state-of-the-art abstraction methods, but also more recent work from our research team. It offers a common framework that, thanks to its implementation using JuMP and MathOptInterface, and it's also highly modular and benefits from not only the power but also the convenience of Julia, as you all know. And for future work, well, first we have to solve the remaining issues on the GitHub, of course. We also want to implement the orchestrator that I just mentioned, and we also want to benchmark Dionysos on a more practical problem, which is the bipedal robot we have in our laboratory. So thanks a lot for your attention, and if you have any question, please ask.
Yeah, so for the questions, please ask them, and if you can repeat them, that would be very nice, because it's also in the recording. So, any questions?
Yep.
Is Dionysos limited to discrete time models, and what about bounded disturbances?
Okay, so the question is Dionysos able to tackle only discrete times control problem or even continuous time control problem? And so, and also about what about the disturbances? So, in fact, for now, some solvers are able to tackle only discrete time control system, while others only for continuous time systems. But in fact, so what we would like to add now is simply just a box that will given a continuous time system, we'll translate it into a discrete time system and then apply all the algorithms that could be applied on discrete time system. So we just want to add this to bridge the gap between the two kind of systems. And about the disturbances, so now in Dionysos we are only able to manage bounded disturbances. So we are not talking about distribution for the noise, but we just consider that the noise is maybe contained in a polytope centers at the origin.
And the reason is that we
Can you speak in the microphone?
And the reason for that is that we only use automata to abstract dynamical systems. But if you have distribution on your disturbance, then it becomes a stochastic system, and you need Markov chains or IMDPs or this stuff.
Any more questions?
Sorry, this is not exactly a Julia question, and I don't know anything about system control, but on your slide comparing Dionysos and the other systems, there were these like discontinuities when the thing was like doing the sharp turn, so sometimes it like went and then it did like a dip. Do you know what that is? Yeah, like here, on both sides.
So for example, this one.
Yeah, exactly, yeah.
So the question is it normal that in both solutions there are these discontinuities? Well, I think it's one of the consequence of abstraction-based control. So the method is such that it uses it chooses to go from this state to the state on the left and then continue. But maybe if you use other control method, then you wouldn't have such discontinuities. But in fact, it's the discrete nature, I would say, of the solver that leads to these kind of behaviors.
I will maybe just add that, okay, it's probably maybe because of the discretization. Maybe if we reduce the size of the discretization, this kind of behavior will disappear at some point. Yeah.
Yeah, also, it's a whole field of research how to discretize the state space in a smart way, and this is the implementation of this 2017 paper, which is what we say a naive way of abstracting the system, because we do a very uniform grid.
I have a question also about this grading in this lazy approach where you have this
Yep.
trajectory. Are you able to refine the grid?
After Adrien, I think.
Yes.
Or maybe after.
Yeah, this
Or this one? Yep.
Yeah, are you able to refine the grid? Maybe some ODEs or some systems might require more refined grading in some.
Exactly. So all the point is, okay, maybe. Okay, so the question is, okay, how can we refine at somewhere in the state space depending of the ODE?
Yeah, are you able to refine some parts of the state space? Because
Yes.
some dynamical systems you might require more, let's say, refined grading.
Yeah. So.
The question is if you can do that or
Yeah.
okay. It's fixed.
Okay, so depending of the ODE, maybe at some part in the state space, maybe big cells are fine enough in order to encapsulate the behavior of the original system, while for maybe some more difficult part of the system to control, because maybe at somewhere the system is not stable or this kind of stuff, then we need to refine the discretization. So, in fact, in this example, we just for now, it was also a quite simple implementation. So the size of the discretization was fixed, okay? But what we only wanted to do is to avoid to construct the abstraction on the entire state space. And so for that, we use a kind of heuristic in order to guide the way that we will construct the abstraction. But on another example, maybe you can go where there is the 5 algorithm. For example, okay, so this is again the example that I just described. And in fact, here we use constant input per cell, so a piecewise constant controller. While, for example, here it's much more powerful. Why? Because here, in fact, we will use state-dependent local controller. And so, if at some places of the state space the system is not stable, because we are now designing a specific controller for this cell, we will be able to contract and to take into account for this kind of behavior to compress the system, and so maybe the cost will be higher because we will have to use higher actuation of the control of the actuators of the system, etc. But we will be able to control the system. Yeah.
Okay, then there's room for one more question.
So you chose to directly access properties on the optimizers themselves. Any reason why you chose that rather than having, like, say, the control as a variable, as a MathOpt variable, and the problem as a constraint, or something like that, and using bridges?
I'll let you answer, Adrien, or you are talking about the bridges in JuMP?
Yeah, the MathOpt interface.
In MathOptInterface.
Like
Yeah.
variable bridges, constraint bridges, objective bridges.
So
Can you repeat the question?
The question.
Yeah, so the question is, why did we use to encode everything as attributes of the optimizers, right? And to define the model itself, the method itself as an optimizer, and not, for example, putting the obstacles as constraints, for example, in the model. And actually, I don't have a very clear answer for you. I would say that this was the way we chose at the very beginning. But the second part of the question was, what about using bridges? If I'm not wrong, bridges, it allows you to have another formulation of your problem which is equivalent to the first one?
Yeah, or relaxed of some kind.
Okay. No, we don't use that for now. We could actually, and maybe it would be nice to investigate the solution and to see if it would be better this way. For now, we just stick to the first version we chose.
Sure, thanks.
Yeah, because our goal is really to be at the end, as in the title of the presentation, as modular as possible for control theory with this kind of approach. So